Hello, my friends. I'm sorry I can't be with you. I am off administering testing, but I wanted to share with you some information on sensation and perceptions. We're going to talk about what those are and how they work together. And along the lines of sensation and perception, we're using a music theme because we sense music and we perceive it. Please take note of what you should be doing this week and where you can get help sessions if you need them. Hopefully you are doing well, but if you have questions, let me know. Let's get together. So, of course, as always, our vision, mission, and Class Connect Fab Four, because you know we can't live without it. And what are we doing today? Well, today we're considering the difference between sensation and perception. And we're focusing on sensation and starting to talk about perception. We're going to talk more about that next class as well, actually, in the future. Sensation is our window to the world. It's the part that refers to any information that comes in through our senses, touch, hearing, smell, taste, sight, all of those. That's sensation. But the question is, once something comes into our senses, how does our brain organize it? What does it do with that information? And what is transduction of senses? For example, if I take a sip of my water, I know I drank water, I know how it tastes, I know how it feels, but it's not like that water actually goes up to my brain. How does my brain receive that information? So that's what transduction is going to help us know. And then we'll get into starting to talk about perception, our mental interpretation of information from our senses. We're not going to go as deep into that this class, that'll be more next, but it is important to consider once that information comes in our brain, what do we do with it? How come two people can be in the same place and have two different opinions or perceptions? So that's the question we want to ask. And today we have the slide of the lovely Miss Ashley, who goes by Nicole. She had a lot that she wanted to say, and I'm very sorry that it fell on the day of my recording. I am going to go to the next slide. We'll do that now. And I am going to pull myself down here, cover up Dobby for a second, sorry about that. And you can pause and read. Miss Nicole had some fascinating things to say. She plays 7 instruments, 6 of which she taught herself, which I thought was amazing. I did want to say that she plays saxophone, both alto and tenor, and I was laughing because my brother played bari sax, and then she plays bass clarinet, and I actually played contralto clarinet, which is even deeper and taller. I was really short when I played it. So she has some fun things to say, lots of cool stuff that she enjoys, especially blowing up the kitchen. So, you know, maybe we're not going to cook together. No, I'm kidding. I'll lift up my thing here so you can take a look at this wonderful Dobby picture that she did, the free elf. And I'll let you, like I said, you can pause and enjoy. So continuing with our music theme, David Bowie, who found Waldo when he was a baby, it just cracked me up. The question becomes, one of the big questions is, have you ever heard, are you left-brained, are you right-brained? When I was a kid, this was like huge. This was kind of a brand new concept, and everybody had to know because that determined how you learned and all sorts of things. So what do you expect of a person who is left-brained? What would they be good at? Generally, we think of things like logic, math, science, the details of a situation, or like if you're planning a party, knowing how many forks you'll need. How about a right-brained person? What would that person be good at? Well, typically more of the artistic and creative, generally the big picture, kind of the maybe putting together words to create images, things like that. But here's the thing, would you be surprised to find out that actually, even though some of us may tend towards one or the other, it's possible that we're not actually right or left brain? And I have a really great video that's going to be in the description of this recording that you can click on, and it'll let you watch, but it's really neat what they talk about with right and left brain. And I'd be interested to hear what you think after you watch it. So you can pause it and watch it now, or you can go back and pick it up in a little bit. All right, right brain versus left brain. Well, here is very specifically What can we expect from each? Sorry, I'm moving around to the other side. So the left brain, as I mentioned, the more academic side, the sequential side, the rational side, analytical, more objective, less emotional. You're able to sequence past versus present and to use logic and find patterns. The right brain person, on the other hand, as I said, tends to be that big picture person, looks at the whole picture, the sum of the whole. Tends to be a little more intuitive, a little more emotional, a little more subjective, and kind of, instead of being able, sometimes they can't always explain why, but they just get it. Things like that, maybe a little more fantasy oriented, meaning like imagination and creativity, although absolutely could be fantasy as well, the genre. So imagine that a person's brain was damaged. So the question is, what does damage to some of these different parts do? And I've got lots of parts listed here, including these guys, Broca's area and Wernicke's area. And so the first question might be, what does the corpus callosum do? Remember that thread that runs between the left and the right hemispheres? It's here. It's just poor. It's kind of drawn strangely. But what would happen if you cut that corpus callosum? Sometimes when people have severe seizures or depressions, that's one of their last resorts. What happens? We'll talk about that. Your cerebellum back here, it controls your motor functions. What if that gets damaged? What happens to you if you suffer damage there? I'm trying to figure out where I can put myself, sorry. And then how about Broca and Wernicke's area? They're really important that we want to make sure we talk about. Broca's area is the area right now that allows me to talk to you. It produces speech. And Wernicke's area is the part that allows you to receive what I am saying and understand it. That is the part that receives speech. So anytime there's damage to the part that produces speech or receives speech, this damage is referred to as aphasia. So Broca's aphasia would mean that a person could receive speech and understand what you're saying, but they might not be able to produce it. And then Wernicke's aphasia would be the opposite. They might be able to speak, but they can't really understand what you're saying. All right. So what gets the attention of your senses? Believe it or not, there's like 100 things that happen around you every day that you probably don't even notice because your senses don't even pay attention to it. Well, what gets the attention is the stimulus and response. Okay, for example, this picture right here. Some of you may have said, "Oh, yay, this is so awesome," and other people might be going, "Not sure who this person is." So there has to be something that attracts your senses somehow. A stimulus is that thing that evokes that specific reaction that attracts your stimulus or your attention. A stimulus is designed to create a reaction. So, for example, you see this person, if you know this person and listen to his music, you're like, "Woohoo, this is awesome, I love the picture." If you're not a big fan of the music, may not be much of a stimulus. If you heard a loud dog barking or something, that could be a stimulus that gets a reaction. A lot of approaches, including neurobiology, behaviorism, and cognitive psychology, focus on our response to the stimulus. How do we respond? And then they use that to decide kind of what responses we need to maybe modify. So we're not going to use our whiteboard tools microchat box, but one thing that I would have had you do is to imagine that you're walking home from school one day when a large dog jumps out at you from behind a tree. He starts to growl and shows his teeth. Do you quickly turn around and walk in the opposite direction? What do? Well, the question is, what is the stimulus? What are you reacting to? Probably that large dog growling and showing teeth. And then what is the reaction? Well, according to this, the person quickly turns around and walks away. But I've had students tell me, "Oh, I wouldn't walk away. I'd whistle, or I'd, try to get the dog's attention because this wouldn't upset them." I've had other people say, "I wouldn't walk. I'd run as fast as I could." So it really depends on what the stimulus, what your response is based on how that stimulus how your brain reacts to it. All right, like I said, there's so many stimulus that happen like all the time around us that we don't even notice, guys. I mean, you'd be really surprised what goes right past you that you don't notice. And some of that's because the stimulus is below our absolute threshold. Our absolute threshold is the minimum amount of a stimulus we can detect 50% of the time. So, for example, there might always be a breeze in my house, but there comes a point at which I'm not going to notice the air moving very much because it's below my ability to detect it. So anything below that absolute threshold is called subliminal. Maybe you've heard of subliminal advertising. It means that it kind of sneaks under your senses and you kind of don't really pay attention to or recognize it. And you can see, I'm going to move myself back up here. You can see that for hearing, it's the smallest tone that can be detected by normal hearing when there's no other sounds to interfere. Have you ever been in a super quiet classroom, like everyone's testing, and you hear the clock? And maybe you've never even heard the clock before, but suddenly you can hear it? Well, that's because now where there's no other sounds, it gets into that range that you can hear. Or vision, the smallest level of light a participant can detect. For example, the normal is a candle flame seen at 30 miles on a clear night. So I don't know if you want to have your dad drive 30 miles away and hold up a candle and see what you can see, but that should be where you should be able to see it 50% of the time. Smell, the smallest concentration you can smell. You know, if I take a bottle of perfume and I spill it on the carpet, you're probably going to smell that. But if I take one drop of perfume and I spray it or squirt it and it goes into the volume of air in a 6-room apartment, that should be the smallest amount of perfume that I might notice. And again, 50% of the time I'll notice. And then taste, the smallest amount of salty, sweet, sour you could taste. Normally is a teaspoon of sugar and 2 gallons of water. Now, interesting fact. That actually is being used now as a way to determine if a person has the possibility of being diabetic. If you take 2 gallons of water and you put a teaspoon of sugar in and you cannot taste it, then there is a chance that your taste buds are set too high, and that's part of why you consume more sugar, because you don't taste the sugar the way that a quote-unquote normal person would. So if you're ever interested, you can set up a science test actually more easily with taste than any of the others, where you can take a glass of water and dissolve varying amounts of sugar into it and see where it is that you find the one where you can no longer taste the sugar. So just something interesting if you're looking for something to do on a Saturday afternoon, or you say, hey mom, I want to do a psychology experiment. There you go. All right. I like that. That cat makes me laugh. So let's talk about sensory adaptation. Let's talk about your favorite song. I want you to think of that favorite song the first time you ever heard it. Maybe the second time you ever heard it. It was awesome, right? Oh, couldn't get enough of it. You just wanted to hear it again. Start thinking about that song around like time 100. Did you still have that same exact rush? Were you still like, oh, I love this song? Or were you like, oh yeah, that is a good song? Does it still hit you the way that it used to? What I'm describing is something called sensory adaptation, where we have a decreased responsiveness to stimuli due to constant stimulation. So the first time we heard that song, the second time, oh, could not get enough of it. But somewhere around the 20th or 30th time, we may have been like, oh, I love this song, but it didn't pull us the way it did the first time. Maybe we were like, I love this song, but I'm going to have to pause for a minute and get my work done. You know, I'm watching my awesome psychology teacher's video. So sensory adaptation over time, we get used to a sense. So certain sights, tastes, smells, etc., we adapt to it over time. And if you think about it, yeah, it makes sense. I mean, maybe the first time you had some beverage or the first time you had a food, oh man, it was so amazing, but now you don't think about it as much. Okay, so we've talked about sensation, which is that information coming into us. But now we got to think about perception. Basically, what is our brain doing with that information? There you go, for my classical music fans. Oh, And I got a password for you. Let me move myself down. There is the password for your ticket out the door for the, I believe that's the week 5. I'll show you in a few more slides. So, like I said, when you take a sip of your drink or something else, that liquid itself doesn't actually go into your brain. It's important, we have it, but it's not like we're actually going to have liquid in our brain. And when I see my best friend or a picture of my best friend, it's not like the picture actually folds up and goes into my head. There's an image, but how does that information get from my eyeballs into my brain? Okay, it's not like I could open my head and pull out like a picture of some sorts. What about a time when Herbie and I go to the movies, we see the newest Star Wars movie, and I tell him, hey, Rey's lightsaber is so cool, it's blue. And he goes, it's not blue, that's turquoise. We saw the same thing, right? How come we're saying it's two different things? That's the concept of perception, what we do with that information. So we're going to talk a little bit about transduction. Sorry, again, I'm having a hard time finding a place to put myself. Transduction is transforming sensory signals into neural impulses. Again, I go back to my water, partially because I'm thirsty. That water that I just felt on my tongue, that sensation I just had of the liquid and the cooling and the little bit of sweetness, the actual water didn't go into my brain, but how did it get from my tongue into the part of my brain that said, ooh, that's water because I recognize this taste and I recognize this sensation. Transduction is how it does it. So information goes from my sense to the thalamus and then to whatever part of the brain it needs to go to. And the process takes in the physical stimuli from the environment and changes it into this electrical message that can be understood and interpreted by the brain. I mean, think about it for a moment. My brain is electric. Let's think about your cell phone. I don't have one of those fancy new cell phones. If I drop my cell phone, which is electric, into water, what happens to it? Yeah, I'm not going to be a happy camper, right? Same thing, I can't just pour the water on my head and my brain works, so it has to somehow take those sensations and turn it into an electrical impulse, et voila, I can perceive it. So I'm going to talk a little bit about some things that we would have done in class. Sorry, we're not here to. But this has to do with perception. Here's the first thing I want to bring up. Guys, let me ask you a question. How do we see in color? Nope. Believe it or not, you have as much idea as scientists do. Nobody is sure why we see colors. Why do I see the green light on my computer, or the blue box or the green box? Or how do I know that this box here is a different color from this box or that box? No one's 100% sure, but we have some pretty good theories. And the first one is called the trichromatic theory. The trichromatic theory says that our color cones in our eyes are made up of 3 colors, red, green, and blue. And by mixing all these colors in different degrees, we can see color, which is great, right? That's how I know this is some sort of light blue and orange and I guess a brown, I might call that one. Although someone might say it's a different color, right? Because perception. But the thing is, you know how sometimes you stare at something and then you look away and it's like you have a picture that sticks with you and you can't figure out why? Well, trichromatic theory only explains very basically how we see color, but it doesn't do anything to explain any other visual phenomena. And that's why we turn to a new theory called opponent process theory. And opponent process theory says we still have these cones that are paired up, but each cone is in a pair. So I've got a red one here right next to a blue one. And when the red one fires, it gets tired, right? And so, it needs a break. And so the other one fires to kind of calm it down, like chill, I got this, it's okay. And that's why when you look away and you look at the wall, if I was looking at the wall, or like a white image or something, you will actually see that opposite image. That is opponent process theory. So opponent process theory does a really good job of explaining after images and other vision phenomena. All right, now I told you that my water, when I drink it, doesn't go straight into my brain, right? But there is one sense that does not have to be transduced. Take a quick guess. Let's see if you're right. It is smell. Think about it. What did I just put up into my nose? Just gas, right? Well, my brain can process that. So when I smell something, that information goes directly to my olfactory bulb and then into my brain for processing. And that's why when you smell something, it's the quickest sensation to bring memory. So when I smell, if I walk into someone's house and I smell a particular item baking, I might say, "Ooh, this reminds me of my grandmother's house." It's because smell, it takes the shortest period of time to get from outside my body, inside my body, and to my brain. All right. Sometimes when it comes to sensation, we need to be able to shut down what we're sensing. Sometimes there's too much, and this goes to something called the gate control theory of pain. Okay, I was in a car wreck about 11 years ago, and unfortunately, I broke my knee. And I will tell you that when it happened, I knew something happened, but it actually took me a few minutes to really feel it. Like at first, I was like, "Huh, well, that was weird." And that is the gate control theory of pain. The idea is that when we experience pain that is too severe, our spinal cord can actually, it's like a gate, boom, it shuts down on those nerves. And it shuts down the sensation so that our brain and body can't perceive it. And it kind of gives us a moment to go, wait a minute, okay, what happened? And kind of organize ourselves and then react. So yes, unfortunately, after a few minutes, I was pretty sure I had figured out what had happened. But initially, that gate control shut me down until I was ready to perceive the pain. All right, split brain. Remember our friend, the corpus callosum? It connects the left and right hemisphere, and it's like a bridge. Information can go from one side over to the other. Well, split brain is when the corpus callosum is cut. Sorry, it's taking a moment there. Sometimes it has to be cut due to seizures. Sometimes it can be cut during an accident or for other reasons. But basically, it prevents the left and right hemisphere of your brain from talking to each other. Okay? It's not a very commonly done procedure. It's usually done at the absolute, they've tried everything else and nothing has worked. But how would split brain affect our lives? Well, when I write something, I pick up the pencil with my right hand. Okay, I'm right-handed. If I want to write with my left hand, which I can do, but it's very slow, the information actually travels from my left brain over into my right brain to tell my left hand what to do, corpus callosum. But if it's split, I might actually have to have my right hand grab my left hand and guide it because all that information is stuck in it. I'm sorry, stuck over here, and it can't travel. So split brain affects our lives because it would stop us from being able to move information back and forth. And actually, some people who've experienced split brain, they would have to say, okay, I want to write a poem. What rhymes with blue? Okay, left brain. What rhymes with blue? Shoe. Clue. Okay, right brain. What fits the rhyme scheme? They literally have to talk through both sides of their brain. And so in some cases, people have even given completely separate answers. If they close one eye or the other, they would give totally separate answers. But it does stop seizures and other really severe mental problems. And again, it's something that's only used when there's absolutely no choice. All right, here it is, your Cycle 1 Week 4 ticket out the door. SNP, sorry, I think I said the wrong number earlier, but remember that password was neuron, that's right. And it asks you to define sensation and perception and explain how they affect each other. So that's what we've been going into, sensation being the information we receive through our senses, and perception being what we do with that information. Okay, and they affect each other because if we didn't bring information in through our senses, we'd have nothing to perceive. But perception controls how we react to or respond to that sensation. All right, my friends. Yeah, what can we say? Beethoven wouldn't listen to his own music. The last thing I would have asked you to do is to tell me what you learned about sensation and perception. So you can do that in your ticket out the door. But I did throw out another little video gem, and I will put that in the description or somewhere that you can get to it. And have a great week. I'm really sorry to miss you, but I look forward to seeing you next week. And of course, I'm back tomorrow or Thursday, depending on when you're watching this, if you need me. So thanks, guys.